Welcome to a second day of our third summer school on the assumptions of physics. Today's session is about physical mathematics, this idea of deriving mathematical structure from physical requirements. And Tobias will be giving the presentation today. As we said yesterday, you can put always questions in the QA, and if there are small clarificatory questions, I will stop Tobias or I'll answer them right away. And otherwise, all the questions are going to be at the end. Please, Tobias, start.
Thank you. Okay. Yeah. As Gabriele said, I'm going to talk about physical mathematics. But for those who might be new to this, let me just mention again what the program is about. So we want to identify a handful of physical starting points from which the basic laws can be rigorously derived. So we might have an idea like a physical idea of infinitesimal reducibility. If you think about classical mechanics, if you have a ball, you can mark a single point on it and study how it moves. And if you know how each individual part of the ball moves, you know how the whole thing moves. So you can reduce the system infinitesimally. And we want to then claim if this is true, then you should recover the mathematical notion of a classical state. But if you had something that is not irreducible, like for example, an electron, it doesn't make sense to study just the part of an electron, then we should end up with a quantum state. But to make such a claim, we really need to rigorously derive all the structures from physical requirements, so from the bottom up. And today, the example that I'm going to show is like you can start with like a principle. Science should be about evidence. Then it must be characterized by statements that actually have an experiment associated to it that can verify that statement, or we will end up with topologies and sigma algebras. So it's a concrete example that I'm going to show today. And first, we need to kind of clean up a common confusion. Like our approach is very different from what you might typically assume. So we are typically used to, if you want to know what's really going on, you just need to find the theory of everything, and everything else is just an approximation of it. So if you don't understand QED, just find out that string theory is a true thing, and then everything will be clarified basically. And this is not an approach that we found out to be very productive. So instead of finding a theory of everything, we instead just try to specify the physical requirements and assumptions, and then derive the theoretical apparatus from that. I don't need to know what is truly going on. I just need to make precise what physical requirements what things I am actually assuming, and then the mathematical structure will follow from that. So like I already mentioned experimental verifiability. We will also see certain geometric structures are related to entropy. Yesterday, we learned a bit about Hamiltonian evolution, matter particles under potential forces, and so on. And yeah, this turned out for us to be the much more productive point of view. So we are not really interested in a theory of everything. So the general idea for us is like if you specify general physical principles and requirements that should always be true, then we want to derive from that a general mathematical framework. And if you have any specific situation, any specific assumptions, then you should be able to recover the specific subfield. So there are things that are generally true, and then there are things that are only true in classical mechanics. And so these are additional assumptions that then allow us to specialize the general mathematical framework. And basically, what I'm talking about today is this general mathematical framework that follows from general physical principles. And I'm going to see how we build up these foundational mathematical structures from physical requirements. So we have these two approaches. Yesterday, Christine talked about reverse physics, where we basically take the theory that we already have, and instead of deriving something new from it, we just find out what are the smallest set of assumptions required for that. But today, instead of taking the laws that we already know and like reverse engineering them essentially, we start from scratch and we derive mathematical structures from the bottom up, but based on physical requirements. So this is essentially the picture. We start with physics, we just specify our requirements, and then we end up with the mathematics that we need. So um, again, I need to stress like that this is a very different approach from what you might naively assume. So, in fact, typically mathematics is just treated as a tool. You just use it to do some calculations, and when the tool breaks, you just ask the mathematician to fix it. This is not something physicists has to do. So even in this book, Lost in Math by Sabine Hossenfelder, where she criticizes the use of math in physics, she still says, I quote here, but we don't develop theories by writing down assumptions and then derive observable consequences in a sequence of theorems and proofs. In physics, theories almost always start out as loose patchworks of ideas, cleaning up the mess that physicists generate in theory development and finding a neat set of assumptions from which the whole theory can be derived is often left to our colleagues in mathematical physics, a branch of mathematics, not of physics. So they still just outsource that to the mathematicians, um, but they're not physicists. So somehow on Wikipedia we end up with this idea that somehow you can start with just math, then some part of math is actually has to do with physics. I guess it's mathematical physics, and then from that physics follows. And somehow math even defines the ontology, what is actually real. That's kind of funny. I don't think any mathematician really thinks that they're talking about, I don't know, um, ontology. Yeah, so if you contrast that diagram with what we do, what I had like a few slides ago, we start with physics. The physics knows what things mean. Mathematicians have given up on meaning, like I think 100 years ago. And then we end up with appropriate math that we need. And we don't start with some math and then find some physics in it. So um, to uh, uh, to give some examples, oh, first, we can't just use mathematics purely as a tool because we literally specify what our physical models are in terms of mathematics. It's not just a tool after you specify what you're talking about, how to get the result you want. You even specify what you're talking about in terms of mathematics. So you really need to know what you're talking about, and we use math for that all the time. So cleaning up the mess is not a thing mathematicians can do because they have to make physical choices, and they are not equipped to do these because they're mathematicians and not physicists. And that's actually not our conclusion. That is the conclusion that we got from a mathematician who was like, I don't know how to clean up your mess because I have to make decisions that I'm not equipped to make because they have physical meaning. But in physics, somehow we haven't accepted yet that we need to make these decisions, and we need to look into the math ourselves. So to prove the point, I will now go through a few examples of wrong math. So unphysical mathematics, decisions mathematicians have made that are not physically meaningful. So, for example, in differential geometry, it somewhat became convenient to define tangent vectors as derivations. So a vector, I think this is actually technically a whole vector field, but it takes a smooth function over a manifold and returns another smooth function. And it's supposed to take the derivative of that function at some point. And this is how in mathematics one typically defines a vector. And then every vector can be written in a basis. So if you imagine you have a coordinate system, you take derivatives in for each coordinate, and these derivations form vector space, and then you can use these as your basis vectors. But the physically that doesn't make a lot of sense. So it's a vector space. You must be able to add these things. But if you imagine you are in polar coordinates, so you use radius and angle for your derivations, what does it mean to add them up? The units make no sense. So the radius would be meters, so the derivative would be inverse meters, but they're definitely not summable. Same thing in phase space, where you have one direction that is space meters, the other one is momentum. These units don't add up. So for us, these things do not even form a vector space. So um, that doesn't really make a lot of sense. It's mathematically convenient and it's very precise, but physically doesn't make any sense. And the mathematicians won't fix that for us. They don't care. They don't need units. We need units. Then another example is on a Hilbert space, you can uh, find a sequence of states. This psi I is basically the ground state with some excited state, and you consider a sequence where the weight of that excited state goes down, goes to 0. So you have a sequence that will end up converging to the ground state. And then you can have an observable. So on that, it's just a simple system where you have excited states on a ladder. And then if you calculate the expectation value for the sequence of states, then you will see that it will end up converging to 1. So that will be the first excited state. But the sequence itself converges to the ground state. So somehow that doesn't match. Maybe the topology that you put there doesn't make any physical sense, but it's the topology that is most natural, I guess, for mathematicians. And but physically it doesn't make any sense. So there's also something the mathematician won't fix for us. We have to find out what we actually want and pick the right topology. So basically, what we currently have to deal with is that, well, we have the physical world, inherently an informal system. Still, our physical objects are well defined, even though they're informal. And then we use math to work with them. So we have a formal system with well-defined mathematical objects, but we have situations where some physical objects just don't map to any reasonable mathematical thing you can. Like if you treat delta as a function, like a Dirac delta as a function, that's not a mathematical thing, but somehow physically kind of makes sense. You might have some meaningful mathematical object, but you slightly modify it, you have a transformation that turns it into something else, and all of a sudden it has no physical counterpart anymore, or all kinds of things can happen. So this map between math and physics is less than ideal, as I just showed. So what we really want is a clean map between the physical objects and the mathematical objects. And as we will see, it's not just that you find like a one-to-one correspondence or something like that. It's really while doing that, while developing it, you also need to your physical specification at each step, the specific thing you assume has to map to a mathematical definition. And I will show explicitly how this will happen. So the slogan for physical mathematics is when physical objects are mapped to the right mathematical objects, the physical specification maps to the mathematical definitions. So we will see how this play out in today's lecture. So really to clean up, to be more precise, we somehow have to develop a standard of rigor for physical mathematics. The mathematicians have their own standards of rigor. But of course, we still have an informal system. We won't fully formalize all of physics. We can't be as rigorous as they are, but still, we need to be more precise when we make this map between math and physics. So this is basically the standard of rigor that we have developed and that we stick to. So first, when for example we define an axiom, this is an example, the axiom of mixture. We will see that again later. But how we start is we start with an informal, intuitive requirement. So that is just something that should make sense to every physicist or engineer. For example, the statistical mixture of two ensembles is an ensemble. If you know what an ensemble is and what statistical mixing is, this is obvious. Of course, a mathematician would say, I don't know what that means. This is not precise. So for the mathematician, we give a formal definition. So we say we have an ensemble space. It has an operation that takes a number between 0 and 1. It takes two ensembles and it gives me one ensemble. We call that thing mixing. We denote it like that. And then it has a few properties. It's continuous, and then so on and so forth. That's something a mathematician would accept. So we obey their level of rigor. So now we have basically something that makes sense to a physicist, something that makes sense to a mathematician. The key point is now that we need to make sure that there is a tight link between the two. So we have to justify every single mathematical definition here, every property, based on the informal intuitive picture that we have. So we don't just assume some mathematical things out of convenience for every single one of them. I have to justify why I put it there. So we have a clear picture of what we mean by ensembles. If they are, we must be able to reliably prepare them. So you have some preparation process that outputs ensemble one. We have a preparation process that prepares ensemble two, and then we are able to randomly select from one or the other ensemble with a given probability p, and then the output of that is just again the output of like now a composite process, but it's still a process. So this is how we justify that there is such an operation that takes a probability, like a value something between 0 and 1, and then it takes two ensembles and gives us another one. This is the clear picture, and this is why the math is the way it is. And then for each of these properties, we justify why we put them there. So, for example, associativity basically tells you if you want to mix more than just two ensembles, basically the order in which you mix them doesn't matter. You have associativity. So in this justification, we explicitly say, okay, you have three processes, and then it doesn't matter if we mix first P1 and P2, or then P2, P3, and then mix it with the last one. So there is a clear justification for why this mathematical definition is there. We do that for every single one of them. So this is how, like, this is the level of rigor that we have developed and that we stick to through the whole book, the part of the physical mathematics. And basically what that ensures is that at each step, there is no question like what the math describes. We don't just like propose some kind of mathematics and then try to interpret some physics into it. Like at each step, I told you exactly what the mathematics describes. And each of them are justified, and you can always check why it's there. That also means that whenever we make any mathematical proof, all the properties that we use in that proof are really physical properties. So you should be able to understand the principle every mathematical proof in physical terms. So there is nothing like just math. Everything is really physically motivated. This is why we call it physical mathematics. It's still mathematics, but we made sure that everything that appears has a specific physical meaning. So really what we want to achieve in physical mathematics is to recover all mathematical structures that we use from clear physical requirements. So we really start from scratch and develop everything, and at each step make sure the physical meaning is clear. So at the end of the day, we should then know exactly where do I use mathematical structures and why? What are the physical requirements necessary to use these mathematical structures? And we then get this perfect map between math and physics. And that would be the general underlying framework for everything that we build on top. And really, we think this is a better way to do physics. It's more rigorous. It's essentially physically rigorous and not just mathematically rigorous. And yeah, things you might usually consider like just mathematical details turn out to be really physical requirements, and we have to think about them more clearly and not just ignore them and leave them to the mathematicians. So at the end of this lecture, hopefully you're convinced that there is nothing like, well, this is just math. If you look into it, you will find what physical requirements were hidden inside of them, and I will also show you how you can recover the math again from these physical requirements. So just to finish talking about this methodology basically before we go to the specific examples. Um, really, we start with mathematical requirement with physical requirements, and we can be both mathematically precise and physically meaningful at each step. And each mathematical structure is justified by the physics. It doesn't just come out of nowhere, and then we found out, well, it kind of works. No, at each step, we justify why it's there. And for physical mathematics, we stick to unavoidable physical requirements that are like generally true because we want to develop the foundational structures that should be developed in all physical theories. So and this is like a really a constructive method. It's very systematic. You don't need to guess um, what kind of physics is represented by this math. Everything is clearly articulated. Okay, so that was the overview. That's basically the methodology. But now we want to see like a concrete example, how we can start with physics and get a mathematical structure, so that you can see that we are not just like we're not just talking. We have actual examples of this working. So what I'm going to talk about is how the logic of experimental verifiability, if you formalize that, basically you get topologies and sigma algebras. So our starting point for that is principle of scientific objectivity. So this is obviously something informal, but this is our starting point. So we say science is universal, it's non-contradictory, and it's evidence-based. So what does it mean? Well, we should, in science, it's about statements that have some experimental test associated to it. If you can't test it, then, well, that might be an interesting statement, but it is not part of science because science is evidence-based. Also, it is non-contradictory. So really, every statement that we talk about should be either true or false. Of course, you might not always know if it's true or false, but there must be only one value, true or false. And then there should always be a test associated to it. And we acknowledge that not every test might always tell me whether it's true or false, but there is at least some. So in general, you might have your statement might be true or false. You might have a test that if the statement is true, succeeds in finite time, or if it's false, it might fail in finite time. But it could always happen that either it takes you infinite time to find out, or your test doesn't tell you. And if we then constrain ourselves to verifiable statements, so that if the statement is true, you know for sure your test will succeed in finite time and tell you that the statement is true, then we call this a verifiable statement. and we're going to study what kind of structure we get from there. So the axioms that we develop, well, first, um, we split them into two steps. First, we just talk about logic, and then we basically talk about what we mean by verifiability. So first, where mathematicians might just start by saying, well, logic, we just assume we have a Boolean algebra, and then the Boolean algebra satisfies some things. Turns out satisfying, like justifying, as I showed before, each requirement of a Boolean algebra is not the most straightforward way for us, but we can still end up with the same mathematical structure, but by just taking a different route. So where at each step it is easier to justify why this should be true in a physical context. So, for example, we start with the axiom of a logical context, which is basically just a collection of statements that have some well-defined logical relationships. And we say, well, there must be a truth function that for each statement assigns it a truth value. So just that there is a well-defined truth value for each statement that I'm talking about. I might not know what the truth function is, but there is one. Typically, what I know is only like some minimal logical requirements. So even before I do any experiment, if I'm talking about animals and my statements are like this animal is a cat or this animal is a dog, I know before doing anything that these two are not compatible. Like it can't be both a cat and a dog at the same time. So even though I don't know the full truth yet, I know I know what truth functions are possible based on some minimal logical requirements that I can already bake in before I made any experiments. So we assign that, and then we have an axiom of closure. If you have some statements, you can basically combine them like with ands and ors and so on. And at the end of the day, all of these axioms will lead to a Boolean algebra. We took a different route such that at each step it was easier to justify in physical terms why these axioms should be true. But then at the end of the day, we arrive at a well-known mathematical structure. What I'm going to talk about more is are these axioms of verifiability, where really the physics comes in, and we actually also at the end of the day arrive at a different mathematical structure, the Heiting algebra, which is something in intuitionist logic, where basically you don't have just a two-valued logic. You basically have true, false, and undefined, so to capture the fact that your test might not always succeed. But okay, let's go through these axioms about verifiability more step by step. So, so some statements in our total set of statements are verifiable. We make some minimal requirements. So a certain statement, which is essentially always true, is verifiable because I don't really need a test. Like just by logic, I already know it has to be true. Same for impossible statements that are always false. Um, and then if you have some statements that are logically equivalent, then they both, if I have a test for one, obviously it's a test for the other one as well. Just by logic, they are essentially the same statement. Um, but the idea is if you have a verifiable statement, I only guarantee that if the statement is true, my test succeeds in finite time, which by the way also means if you take the negation, you're not sure that this is still a verifiable statement because then you might have the undefined case um, uh, if it's true. So and this is actually like simplest example, maybe consider like looking for extraterrestrial life. If there is some, at some point you will find it. If there is none, you might keep looking for it forever. So you might never find out. So that's something that is captured by this basically undefined case. Okay, So the picture is we have all the statements. Some of these are verifiable and they're associated with a test that verifies it in finite time if the statement is true. And note that I'm not really formalizing how these tests work. I want to say just the absolute minimum necessary about how these tests work. And this will already be enough to recover a lot of mathematical structure. And whenever I can, I leave the details in the informal system and only require the absolute minimum necessary to recover the structure that I want. So, for example, one of these minimal requirements for these tests to make sense is that I can combine them. So if I want to talk about the conjunction, the and of some verifiable statements, then if I have finitely many statements like this, and each have a test that succeeds in finite time, then I can test the and of all these statements. So if I have three statements, and in the case that they are all true, I can just run the test for the first one. It will succeed in finite time if it's true. Then I run the second test and the third test, and all of them will succeed in finite time. So the whole thing will succeed in finite time. So if I can test each of them, if I can verify each of them in finite time, I can verify their finite conjunction in finite time. Whatever the specific test is, this is like a very reasonable minimal requirement of how to combine them. And then if you want to look at the or of a bunch of statements, I can still test even countably, so possibly infinitely many, but still countably many statements. So that's a bit more tricky. But if you have a countable or of all these statements, then if this is true, if the countable or of these is true, at least one of them is true. And if I have countably many, it will be at some point, at some finite position in this chain. So the test, the procedure that I can define that will make sure that if one of them is true, I have a test that will succeed in finite time goes as follows. You start by first running just one test, let's say for 1 second. And then after that, you run two tests, each for 2 seconds. And then you run three tests, each for 3 seconds, and so on and so forth. So what ends up happening, if really this statement is true, then one of these at some finite n will be true. And in my algorithm that I defined here, I will at some point run the test for it for some long enough time for it to succeed, because it will succeed in finite time. So basically, I mean, this might not be the most efficient way of doing it, but in principle, I can test this countable disjunction of these statements. So we say that the set of verifiable statements is closed under countable disjunction. So if you, like I already told you, we want to end up at topology. So you might already see where this is going. The only thing is this is only countable disjunction, and for topology you would have arbitrary disjunction, but we're very close. And now you will see in a bit how we end up with topologies. So once you have statements like this, it makes sense to define a basis. Basically, since you have lots of logical relationships with and or, you only need to know the truth value of some basis of statements, and then you can logically derive the truth for all ands and ors. Oh. So we define what a basis is. And then if you assume you have a countable basis, so a basis is basically a bunch of statements. If you know each of their truth value, you know you can deduce all truth values for all statements that you're considering. So if they're countable, that means I can, in principle, go through each of them one after another. And in principle, I have a plan to find out all the truth values. If there would be uncountably many, there isn't even like I couldn't even give you a sequence of experiments. I couldn't give you protocol, what to test to find out everything. There will always be infinitely many things I will never be able to reach. So let's say we have a countable basis of statements, and in principle, each of them have a test, and I could run them all um, uh, and then deduce the truth values of all statements I wanna consider. Of course, I don't want to make a finite cut. You can always run another test. So infinitely many, but countable. So we define what an experimental domain is. This is basically something that has a countable basis. And then if I know the truth values again, I know the truth values of my experimental domain. And once I consider this space to have a countable basis, then the fact that I only had countable disjunction here basically doesn't matter because I can always reduce an arbitrary disjunction out to a countable one. So basically, I now have my verifiable statements are closed under arbitrary disjunction. And this basically, this is how we will end up at topologies. So the next step we need to do is so far we only talked about verifiable statements. There are still more statements that are not verifiable but still meaningful, which we then call the theoretical domain. Before that, we talked about an experimental domain. And theoretical statements are now closing the set of statements under negation as well. As I mentioned before, the negation of a verifiable statement is not necessarily verifiable. It might only be falsifiable. If we now close our statements under negation as well, we will lose for some statements verifiability, but it's still, we have at least a test associated to each statement. We will have statements, we will have testable statements for which there is no test that succeeds at all. But at least there is one. So the statement at least makes sense. And this kind of closes our space now. And the experimental domain is contained in this theoretical domain. Okay, once we have that, we can basically now talk about, in the topological sense, it will turn out to be the points. So once we have that, we can talk about the possibilities. A possibility is basically something that will define the truth value for everything. Once I have the specific possibility, I know what each test will tell me. So since we have a finite accountable basis, basically a possibility just needs to assign a truth value for each of these statements. So they're basically a sequence of truths, true and false. And each of these sequences will define one possibility. And these are really like each possible cases that we could encounter by running all these experiments in our basis. So technically this is called a min-term. Okay, so the link that we have developed, so I started with verifiable statements. I showed that they are closed under finite disjunction and, well, first countable, then arbitrary conjunction. I might mix them up. I always forget which one is which. But those are the basic the axioms of a topology. So open sets are closed under finite conjunction, arbitrary disjunction. So the verifiable statements basically represent open sets. Then the theoretical statements are Borel sets. So for that, we have closed them under negation, which is basically the complement. And then we get the Borel sets, and then the possibilities will be the points again in the topology. So we have, this is the map that I was talking about between physics and math. we have just specified um, what we do in physics, that we need to talk about statements that have a test associated to it. I clarified some of these are verifiable, some of these might be only falsifiable, and so on and so forth. And uh, this is captured exactly by topology and by sigma algebras. So for example, um, all the true statements that succeed in finite time, this is basically the interior. That's a topological definition, but it now has a clear physical meaning. The exterior um, then corresponds to the falsifiable part, and then you have a boundary where you might have undefined, undecidable uh, statements. So these topological definitions now map directly to physical, to something physically meaningful. So maybe like a few examples if this was too abstract. So you have an open set, let's say between 509.5 and 510.5. It's open, so you say it's before 510.5 and no, yeah, and after 509.5. And then the physical meaning could be, well, you can verify that the mass of the electron is 510 plus minus 0.5 keV. Um, but then if you take a closed set or basically a singleton, that would be the mass of the electron is exactly 510 keV. Uh, you won't ever be able to verify that because it's not an open set, but you can falsify it by basically verifying that it's uh, it's in an open set that doesn't contain 510, right? So or if you want go to the extreme, like let's say you take the rational numbers, that's still a Borel set, but you will never be able to find out if the mass of the electron is a rational number. That would be an example for an undecidable statement. So really we can translate what might initially seem like a pedantic mathematical detail into something physically meaningful. We all know that you will not be able to verify that the mass is exactly this value. So this is very nice. We have now a very tight map, and we can basically translate directly between math and physics. So also one thing we learned from that is that really, if we have this countable basis, so we think about a space that we can explore step by step, then our basis, the possibilities, are sequences of true and false. Really sequences. There is no continuum, and you can just translate that true and false, basically 0 and 1. So each of these possibilities, each of the points in our space are the sequence of zeros and ones. So these are, you can think of them as numbers in a binary expansion, and then they would be between 0 and 1. And that tells you that the cardinality of our set of possibilities can be at most that of the real numbers. So at most that of the continuum. Um, so from very minimal requirements, we find that any higher kind of cardinality that you might consider that mathematicians might be interested in already that's already too much to be relevant in physics, really. So these issues about higher infinities and so on are really something we can leave to the mathematicians because we don't need them in physics. And also, you directly avoid common like pathologies like the famous Banach-Tarski paradox, for example, where you can mathematically you can take a sphere, you can divide it into I think 5 or 6 subsets, and I think you only need to rotate and shift them. You can recombine them into 2 spheres and they will have each the size of the original one. And like mathematically, this you can just define that. But we just avoided all of these issues without even explicitly necessarily thinking about them, because these sets that are involved in this process, they are not measurable. So they will not be a Borel set. And so we avoid this paradox automatically. And it wasn't even that hard. It just came out of very simple physical requirements. So yeah, this is all very nice. And you can it fits really very well with physical intuition. So for example, now that we have topologies, we can talk about maps between the spaces. And what you find very directly. So for example, we can basically interpret what continuity really means. So you might consider an example of the density of water um, versus its temperature. So you might know the density peaks at 4 Celsius, and well, it's essentially a parabola, at least in good approximation, but it's definitely a continuous function. So, and the fact that we have a continuous function means, let's say I can, let's start here. We measure the water density and we find out it is between 999.8 and 999.9 kilograms per cubic meter. So I can verify that statement about the water density. So if we look at the graph, we have this open set here. And then if we basically map that backwards, we get two open sets about the temperature. So if I know if I verify this statement about the water density, I basically verify this statement about the water temperature, namely that it's either between 0 and 0.52 Celsius or between 7.6 and 9.12 Celsius. And this the fact that really this verifiable statement allows me to conclude that it implies this verifiable statement is because if you map the points, this map is a continuous map. So really these inference relationships, if I know something here, I can infer something here. You have them if you have these causal relationships about the points that are continuous in this topology that we defined. So maybe you would be used to, like in physics, to just assume continuity because it's nice. Ideally, we would have, maybe we want more than continuity. Maybe I want something highly regular, ideally analytic, and you would just assume that because it's convenient and it makes everything nicer. Well, the continuous map that's not just like for convenience. Really, it's about connecting verifiable statements in this way. So um, you will once you get a hang of it, you can interpret many properties um, uh, in this way, and it has direct physical meaning now. Even if you go like to some edge cases. So for example, we do have sometimes discontinuous features in physics. So for example, during phase transitions, typically properties of your system have like discontinuous jumps. So for example, if you take the specific heat, yeah, this should be water. It jumps during the phase transition here. But so this is discontinuous. But basically, this is discontinuous in the standard topology that you put on this on the temperature, basically. But the thing is, you can verify that you are in a phase transition. So, for example, if you take a phase diagram here, there are special points, like the triple point, for example, where you can verify that you are at the triple point. We even use it to define the temperature scale. As far as I know, I'm not sure if they changed the definition yet, but you can use the triple point to define your scale. So you can definitely verify that you are at that point. You will see all three phases basically coexisting. So this singleton in the standard topology is not an open set, but the physical topology really that tells me what is verifiable and what is not would include that singleton, and that will change what we mean by continuous. Um, then it's not really surprising that in the Senna topology it's discontinuous. You see this jump, but if you clarify what topology you are using, you can still have a topologically continuous function, but well, we might not be analytic can continuity. You basically got to clarify what uh, topology is the correct one. So this framework is very flexible, even if you might think, oh, but I have discontinuous um, functions that I use sometimes. Well, maybe you should consider again what topology you're using. So yeah, this is very flexible um, framework, and so far it made a lot of sense in every case that we consider. So to summarize that, like I showed on general grounds, how starting from experimental verifiability, we end up with the topologies. We really started with physics and ended up with math. Um, every step in between every proof that we made all uses arguments that are physically justified. So you can really understand many things now, like about limits, which are based on topology, um, topological distinguishability. If you know, for example, like in a Hausdorff space, for every point you need to find, for every 2 points you need to find two open sets that separate them. You can start talking about interpret that as experimental distinguishability. I will always be able to distinguish two cases. I already talked about interior, exterior boundary becomes verifiable, falsifiable, undecidable. So really very nice map. And then the sigma algebra, which is the foundation of measure theory, so specifically probability measures, is very natural because we assign probabilities to statements that have a test. Um, so this leads to many more things. So it is really possible to develop a foundation of physics that's mathematically rigorous and physically meaningful, like at the lowest level you can imagine. Topology is usually one of the first structures that you define, and then you might define higher things on top, like I don't know, manifolds, differentiable manifolds, and so on and so forth. So now we have a very nice map. There is no doubt what the topology now represents. I don't have to interpret it. I right from the start I told you what I want to represent with that topology. And that also shows that really even the lowest structure that probably most physicists have never deeply looked into, like the topology, like most physics majors won't take like a topology class. But even at that level, there was nothing like, I'll just leave that to the mathematicians. It has like very direct physical meaning. And really, either it has physical meaning or we should ask ourselves why it's even there. So we, even at the lowest level, the math comes directly from physical requirements, and we had to just look deeply what they mean, and then we were able to recover them. Yeah, let's see. Let's then wrap this up. You saw we have a quite different approach to the foundations of physics. We don't interpret the math that is already there. We didn't start defining a theory of everything that tells me what is true. really I talked about what we do, how we model the world, and then I just clearly specified what I assume in my model, and then showed you how the math follows from that. So really picking physics at this starting point. Um, that was the lowest level that we start off. We are rigorous, we're precise, but at each step, um, the physics was clear. So it's not like you just try to first be mathematically rigorous and then later you try to make sure, like try to interpret it, put the physical meaning in afterwards. We were at each level both mathematically rigorous, but also physically rigorous. So telling you at each step what things mean. So we really think this is a much better approach. Instead of developing huge mathematical frameworks and then trying to find out what kind of physics they could model, uh, we developed the smallest part first, just the topology. And now everything is clear physically. And now we do the next step. We add more structure, and at each step make sure it makes sense. So that fits with, it's called Gall's law. If you want big systems that work, um, then you got to develop them from small systems. Big systems that work evolve from small systems that work, never from big systems that do not work. I can't take the full mathematical structure, all the layers, and then try to somehow fix the physics. Like I see if I take all the sets, I can't put a measure on them. I get the Banach-Tarski paradox. We're just internally confused at each step. I build them up and I avoid that kind of stuff. Okay, so that was like the general introduction to physical mathematics. In I guess half in an hour or half an hour, I will get into more details. I will give you more examples of what we can do. Remember, you can always find our stuff on the website. All this stuff is in the book. We also recently had a reading group where we went through this in more detail. It's also on YouTube. And with that, we can open questions.
Thank you, Tobias. So let's go because there are already a couple of questions. Should causal functions be measurable functions instead of continuous? Continuity might cause some unphysical problems.
Let's see. Okay. Should causal, okay, we have a causal relationship that is
So why
continuous.
they should be continuous instead of measurable?
Why? So either we assume, so basically, continuous means if I have, um, if I have this map, so we are talking about this bottom layer here, we have a map from X to Y. Then if I take a set here that is open, meaning I take a verifiable statement here, then if I look at the pre-image here, then this is also open, verifiable. Measurable would mean if I take a measurable set here, which could be verifiable or falsifiable, then I get another measurable set here. But really what I want is that if this is verifiable, meaning I can verify that I have one of these cases, so like this case here, 999.8, then I can infer something that is still verifiable. So really, I'm not sure exactly how to interpret measurable here, but really because I want to say like if I can verify this statement, oh sorry, if I can verify this statement, then I want to be able to verify this statement. So if I have an open set here, it must lead to an open set here. So this is immediately how I get continuity. I'm pretty sure we
Right.
could interpret measurable as well. Like right, like off spot, I'm not sure.
So I can do that. A measurable function would basically map a statement that has a test to another statement that has a test. The problem is that the two tests wouldn't agree on terminability conditions. So, and that would be the problem because then you say, oh, I'm verifying something with a test here, but I'm saying that in the other space, that same statement, the logical equivalent statement is falsifiable. No, the statement has to be if it's falsifiable on one side, has to be falsifiable on the other side because they are equivalent statement. We should also note that every continuous function is automatically measurable because again it's mapping statements with tests to other statements with tests. It's just that it has the extra condition that it has to map verifiable statements to verifiable statements. But the continuity here is the topological continuity. So you can put different topologies and you would have a sort of a different notion of continuity based on the topology as Tobias showed when you have phase transitions. So sort of analytically, the functions that we saw before for the heat capacity is not continuous, it's measurable in the topology, the standard topology, but for us, we want to say that it's continuous in the correct topology that maps experimental verifiability. Next question from Filippo. Since experimental distinguishability is required, are all topologies you deal with based on Hausdorff spaces?
Um, so okay, I haven't given you uh the full statement, but yeah. So the fact that we have, for example, a countable basis means that our topological spaces are all second countable. And then what you talked about, he asked about Hausdorff, right?
Yeah,
So I gotta remember the names. T0 is called Mogorov, right? Or is it Hausdorff?
it's called T0.
Yeah.
Hausdorff is T2.
Okay, Hausdorff is T2. I think some people call T0 called Mogorov. So
Kolmogorov, yes.
yes. Um, so it's not Hausdorff, it is just T0 Kolmogorov. I think Kolmogorov just says if you have 2 points, you will find an open set around one that it excludes the other. So if I have two possibilities, then I have then I can verify that I have one and not the other. But I think House of would be stronger. I would have two disjoint open sets that around each point. That will be a bit too much. If you want to know the details, all of this is in the book. So yeah, we have more requirements. And it's T0, it's not house stuff.
Yeah, I can go through them. So we have
Yeah,
cycle countability from the countability of the bases.
yeah.
The space is T0 in the sense that if you have a point, if you have 2 points, you can find an open set that contains one but not the other. And actually, it was argued by somebody who reached out to us that it's not just T0, it's also a sober space because it can be embedded in a locale and other stuff. And that actually is not in the book, it's something that we should add, but technically they are T0 sober spaces. And we do have a counterexample that it's not Hausdorff. So, for example, if you want to know how many fundamental particles are there, the only verifiable statements are there are at least n particles, right? So once we see that there are three fundamental particles, we have verified that there are at least three, there could be four or five, and that we haven't seen. And so the topology is actually the sort of the right-hand topology of all the open sets are the ones on the natural numbers that are this element or greater. So we do have an example of a topology that it's not Hausdorff, that it's physically relevant. Another one, it's sort of semi-decidable question, so something like there exists extraterrestrial life, the possibility are yes or no. And if it's yes, we can imagine that it's verifiable because at some point we'll find it, and then we have verified it. But there is also the case where we keep not finding, and there is none to find, and that would be there's no open set. It would be just falsifiable and not verifiable. So there are cases in which the topology is not Hausdorff. And yes, there are kind of weird cases, but in principle there are, and so we shouldn't just assume that we have Hausdorff. Let's see if there are more questions on the topics that we looked at today. In the meantime, I can comment on a question that was put on YouTube about PDEs, suborbital spaces, and what are the correct spaces for sorry, for partial differential equation. And the short answer that we don't know yet, and in some sense we are starting to understand the problem better in quantum mechanics than in classical mechanics. Just because the math is set up different, and we can use some properties of observables to get these. But it's really the problem of choosing the right space and the right topology. So in quantum mechanics, as Tobias showed, you can have a sequence of elements of a Hilbert space that converge to a particular state, but the expectation value of the observables do not converge in that to the value of that state. And this is exactly where the topology that we have is not the correct one. Because if the topology comes from experimental verifiability, we must have that when a state, a sequence of states converges to a state, all the expectation value of all observables converge to the expectation of those states. Or another way to say it is that if we make a small modification of the state, we better be making small changes in all on all the observables. Like, it doesn't make sense. Oh, I changed the state just a little bit, but the position now is infinite instead of just being a small variation. And so all these problems are basically a problem of understanding what is the right function spaces that make sense, because those are the ones that give us finite, well-defined expectations. And you have the topology correct, so that when you're making the limit on the states, you're making also the correct limit on the of the observable as well. And then essentially finding maps that map valid states to valid states, so that you are always inside remain always inside the space, and then the solution of the PDE would actually be a trajectory within that remains in that space that has nice property, right? So basically that's the idea. And we're still trying to understand exactly what are the requirements, and ideally we would like to exactly have the requirements set in the way that I said before. We have states, we have things that we measure, and we need to be complete and continuous with respect to the topology of that generated by those verifiable and physical quantities. And these are basically the things that we have to still work out.
There's a new question.
Okay, let me go through the question that we did. Could you define or connotate a physically based property?
I'm not sure if that question makes sense to me. Physically based property.
I think to us, it's basically a property that can be verified experimentally. I think in the next talk you're going to talk about continuous quantities, right?
Uh, First I will talk about how to get the standard topology on R
Right.
mostly,
So
and then about entropy mostly on ensemble spaces. So I'm not sure we get into properties. I'm not sure if property use it in the sense that we use in the book, because there we do talk about properties later after we define this stuff. Um, but yeah.
yeah, so we basically say that a property is like something like the color of the beak of a bird, or the color of the sky, or how many coins you have in your pocket, like something that you can go and experimentally test. Oh yes, the value of this property is within this range, or it's exactly this value, and uh, and that basically becomes some type of topological space, and then the map from whatever set of states or configuration that you have, the map from that to the physical property has to be a continuous function, because you are going to be able to characterize verifiable statements on that space based on the property. And so for us, it can be essentially anything, and again, it fits in the general structure of topological spaces. But most of the time, it's going to be continuous quantities, and we have a way to uh, derive continuous quantities from the notion of these quantities before this the distance is before this mark or is after this mark, and so on. And Tobias will talk about it later.
I can just add that property is more general than quantity. I mean, so when you use the term value, which is true, but people shouldn't necessarily associate a numerical value. So as one of the examples you just gave, you could talk about color, and that would be a property that you can experimentally verify that's not associated with any numerical, with any quantitative value. So our properties are more general than things that are quantifiable using numbers.
Yeah, in terms of the phase space diagram that we saw before, that the object, the material is in a phase transition. That's a property, that it's a yes/no property, or what phase you are in. If you are in a gas, or all of those are properties that are not numbers. Oh, there were some comments on the YouTube chat that I. So Julius says, in manifold theory, our space-time is usually assumed to be Hausdorff. So are you saying that non-Hausdorff space-time is also possible? No. Once we have the topology generated by something that is locally a vector space, for example, that's gonna be automatically Hausdorff. It's once it's T0, for example, vector spaces that have a topology that it's comparable to a vector space. Once they're T0, if they're second countable, they are automatically metrizable. So you jump a lot of steps. And so again, it's this additional structure that gives you these other properties. So the spaces that are not T0 are very few, and they're there, but probably for a lot of, like, once you have continuous variables, they effectively disappear.
If there are no new questions, I think I just understood the first question a bit better. Maybe I can add something to that. He asked about what about measurable functions. So I think a measurable function would be it could take a set here that is not necessarily open, but it could also take an open set here and then map it to not an open set, just a measurable set. So basically something not in this dx, but our d bar x. So there will be then there is still a test, but I'm not sure if it finishes in finite time. If I have this map though, then I have here a test that does succeed in finite time, and I have this causal link between these two spaces. So I can just use this test here. Like I can test the water density to find out something about the temperature. So if I have this test that succeeds in finite time, and I want to find out if the water temperature is between 0 and 0.52 or 7.6 and 9.12, then because there is this causal link between the temperature and the water density, and I have this test here that succeeds in finite time, I can use it as a test on the water temperature. So the thing will be then an open set. If it's not, I should update my topology and make this an open set, basically. So whenever you find, just like you found like in the case of the phase transitions, you found this jump. Well, the fact that you found this jump, you have this discontinuity, you can use it to find out that the phase transition is happening, right? So you basically have more tests available now, and that means you have more open sets. You can verify more statements. Yeah.
Yes. So at this point, if people want to ask more general questions, they're free to do it. Otherwise, we can take a break earlier. Okay, let's take the break earlier then, when we'll reconvene in 10 minutes. Okay, we are ready for the next session on some results in physical mathematics. Tobias, take it away. And Tobias, you're muted.
Yes. Sorry. Okay. Okay, just to quickly give an overview, we are talking still about this general theory. I talked a lot about experimental verifiability, and I will talk a bit more about information granularity and states in a bit. But this is all the general theory that will then um, serve as a basis so we can make claims like infinitesimal reducibility will lead to classical phase spaces and so on. We're still working on the general theory here at the bottom. So, what I'm going to talk about, or what I already talked about before, was this link between experimental verifiability and topology in sigma algebra. That was basically like an abstract connection, experimental verifiability and topologies. Now I'll make it more concrete and show how really by saying what can I experimentally verify, what specific topology I get. Specifically, I will show how you can end up with a topology of the real numbers. And I will start from what I can experimentally verify. And after that, I'm going to talk about ensemble spaces. That will be another example. So, but first, I'm going to give this concrete example. How do we get the specific topology of the real numbers? So that's the task of this part, how to recover the reals. First, we need to know what are the real numbers, how are they actually mathematically defined. And there are, in fact, many ways. So there are, maybe you've heard about Dedekind cuts or Cauchy sequences of rational numbers, whatever. These are all equivalent definitions, and we got to pick one that is most convenient for us to recover. So basically the route we will go is through the order. So also when I talk about reals, I only really talk about their topology, and I don't care about the field axioms of it. So addition, multiplication, and so on. Basically, the topology of the real lines is defined by the order on the real lines. So once you have an order, you can define topology by this order relation. So we all know, like, if Q less than B, this is an open set. So if you know the order, you know the topology. So we don't really care about distances, which would require, like, a difference. But we don't care about this. We only care about the topology in this case. So the characterization of the reals that we use is based on Cantor's isomorphism theorem. So we characterize it as a type of linear order. So it says every countable, dense, linearly ordered set with no ends is order isomorphic to the rational. So, and then the completion of a linear order is unique. So what do we need here? First, the rationals. Countable means, well, we can count there's a bijection with the naturals. It's dense, which means we can always have an element between two elements. They're linearly ordered, so every element is before or after another one. And we have no greatest or smallest element, so there are no ends. And then the completion will then be unique. Once we have the rationals, there's a unique completion, where now every subset has a primum and an infimum. So then, so once we have that, every complete linearly ordered set with no ends that has a dense countable subset is order isomorphic to the reals. That's basically the route that we will take to recover them. So we take this as our definition essentially of the reals. So really it's about order, and this is what we will have to recover, and we have to so we will define how does this order emerge from what we can experimentally do. So the core notion that we have is that of a reference. So that's very general. It could be many things. I like to think of it as the notch on a ruler. So you might imagine the ruler going like this, and then this is the notch on the ruler, and then you have, in principle, you could have things before it. You could have something on the specific notch on the ruler or after it, and then that might in principle be overlap. The only case you cannot have is that something's before and after, but not on. But this is basically the model that we have for each of the experimental tests that we are considering. That these are basically the statements that we can verify. So the verifiable statements that we define are just of this type before or after, and then there is this on case, which is not necessarily verifiable, but before and after are. And so this is the mental model we have for the experiment, for the type of experiments we can do. And now we are asking what kind of properties do these tests need to have so that they are ordered like the reals, and then we will recover the topology that we're looking for. So to formalize this, we say when you have a reference, those are basically, it's defined by three statements: a before statement, an on statement, and an after statement. And then we put some minimal requirements on them. We can verify that something is before or after reference, so B and A are verifiable statements. An object can be on, so this on statement is not impossible. That's what this means. If it's not before or after, well, then it has to be on. That's what this means. If it's before and after, it also has to be on, like in this case. That's excluding the fact that it is not on, but before and after. So this is basically a single reference, this triple of statements with these requirements. And then, yeah, we can also define what the beginning and after reference would be, something where you cannot be before it or you cannot be after it. So the first requirement that we put on these statements in order to get to the reals that we need to require is that the reference is strict, as we say. So that really means you're either before, either after, or you're on. And all the other cases are excluded. So basically, physically, what that means that we are assuming whatever we're measuring is like a point particle, or at least we assume it is so small that it is much, much smaller than the width basically of this reference. We have to assume that. So then we call this reference strict. Then, of course, this will be only one notch on a ruler. A ruler has many of them. So if we have a whole system of references, they are all related by each other. They are ordered. So what we need to get a linear order is to assume that we don't have things like this where you could be before one and after one and the other way around. So you could be, in this case, being before the second reference and after the first one, but you could also have the opposite case. Then there is no way of putting an order on these references. So the next step is to require that these references are aligned. What do we mean by aligned? So basically, we need to be able to say if something is before one reference, then it is not after the other. So we have implications between the before statements and the not after statements. So in fact, the full chain is like this. If you are before the first one, you are also before the other one. And it also means you're not after the first one, and you're also not after the second one. So the picture looks like this. And now these arrows here, that's what we defined before. I haven't explicitly mentioned it, but this is basically it's a narrowness of a statement, meaning but it's essentially implication. So the order that we kind of put in here really comes from the order of statements in the sense of implication, which is quite nice. Really, those are a priori different relations, but now they become essentially the same. So now we next assume these references in our system are aligned, but this is still not enough. We need to somehow make sure that we can fill the whole region. So whenever we have two references that are aligned, well, there are in principle, or yeah, when we have two statements, there are two cases. They can overlap, like this whole picture, or they cannot overlap, like in here, and we will know what overlap means based on the implication of these statements. Or if it's possible to be before the second and after the first. And in these two cases, we need to make an assumption, or we need to require that we can put something in between. So the last thing we need to require is that these references or these reference systems are refinable. So if you have two overlapping ones, you need to be able to stick one in between to distinguish this overlap. And if you have two that do not overlap, you basically just need to require that you can put something in the middle. So that's what we mean by refinable statements. And that makes the third requirement. And then you need to go through a whole bunch of proofs. But you don't need more requirements than these. But then at the end of the day, you can prove just on this, based on this, that you get the order that you want. And in fact, these three requirements are necessary and sufficient. So really, you need them to be strict, aligned, and refinable. And then this is all you need to get the linear order that you want. And then at the end of the day, this is how you will get the topology. And also, the distinction between the integers, which are also ordered, and the reals is just that for the real numbers, you can always put something in between. For the integers, there can only be finally many things in between two references, and between some there's nothing in between. So that's an explicit example where you started by explaining what is experimentally verifiable, what statements you can verify, and then you can directly construct the topology, and it is the standard topology on the real number. So this is a concrete example of what I introduced in the first talk, more abstractly. And one of the interesting insights is that well, these are all quite idealized. Like you can only you need to assume that whatever you're measuring is basically point-like, and then your references need to be extremely stable and aligned. So these are very idealized, and like in classical mechanics, if you study the motion of a particle, you assume it to be a point. You do assume these things, but those are idealizations. But the point is, if you have to give up any of these, so if you really want to consider the fact that, well, if you have clocks that are not perfectly stable, so they somehow move and you cannot perfectly synchronize them, and you can make these ticks as small as you want, you will basically very quickly lose the order of the real numbers. So they will not be necessarily consistent before and after. So when you give up any of these three assumptions, you quickly end up with a drastically different model, and then it's not obvious what kind of mathematical structure you might want to still be able to say anything. So that also means by looking at like what assumptions are hidden in the real numbers, you find out uh, what do I need to do if any of these assumptions are not true. And it turns out we might need very drastically different mathematical models. So you might imagine that you have references and you have basically uh, so you can say this is still before this is still before this. You can also say this is before this, but you don't know which of these becomes before or after the other one. So and then really like the topology is very different, but some of this also only happens. We would expect this to happen at very small scales. Like if you have, I don't know, a large distance, you will be able to tell what is before and what is after the other one. But somehow, if you get very close, you might not be able to assume anymore. You have proper order. So, what we might be looking for is something that on large scales has a topology that we know of the reals, but at small scales has a different topology. And that is something not very common in mathematics because usually you have somewhat of a clear cut between topology and geometry. But having a topology that basically changes based on distance, so it's at large scales, you have essentially a topology of the real lines that comes from a linear order, but then at small scales, it's a different one. There might not be math that is already suited to model something like this. But based on the physical intuition that at small scales you might not be able to distinguish anymore what is before or after the other one, would suggest that we need something like this. But yeah, this is definitely something we're not ready to attack yet. So to wrap up this part, the real numbers and their topology can be recovered from an idealized metrological model. Really, the ordering directly comes from the order of the statements, basically implication. So so if you say 3 is less or equal to 5, then you're saying the implication goes like this. If there are less than 3 items, that implies, no, the other way around, implication goes left. If there are less than, sorry, no, it goes right. I got confused. If there are less than 3 items, that implies there are also less than 5 items. So the order on these numbers comes from this arrow, like the implication. So they're actually very naturally you can convert one into the other. But what we have seen, the assumptions that were necessary to make, they were quite idealized. So we had to make quite strong assumptions to get this specific ordering. The continuity basically from if you want from rationals to reals, that was not really the hard part. So if you have to give up any of this, you will not just give up continuity or anything, you will lose the linear order. And then things can get much more complicated very quickly. Okay, that was the first part. Now we get to a different part, which will be about ensemble spaces, where we basically try to find general notion of state, so generalized state spaces. This is all. This is actually a specific project funded by the John Templeton Foundation. So what we consider here is well, we start with another principle, and principle of scientific reproducibility. So we are seeking like a notion of state, but first we acknowledge that we actually never talk about the specific state at a specific instance. Since we're doing science, everything we do has to be reproducible. So you're actually not talking about the single instance. You are always talking about something that in principle can be reproduced, and you're talking about the whole collection of possible outcomes of the same procedure. So if I make a claim about a certain state, someone has to be able to reproduce that, reproduce my method of preparing such a state, and what I'm saying should hold for all of them. So I'm really talking about the whole ensemble, because everything has to be reproducible. So really, the mental model that we have is you need to have a procedure that prepares something, and that initial ensemble is the collection of all the possible outputs of this procedure. Then might have some physical process that turns this initial ensemble into a final ensemble, but it is still an ensemble. And then you have a measurement procedure, and you end up with some statistical data. So really, we talk about ensembles all the time, and we talk about statistics. And of course, this is something that every physical theory must describe. It must describe which ensembles are possible, because it will have to talk about things that are reproducible. So this is our starting point. This is why we look at ensembles and not at like individual states, like points. So the examples will be, let's say you have a classical discrete system that you just have basically each ensemble is a probability function. So each entry here just gets a probability. If you have a whole continuum, for example, you have phase space with some symplectic form on it, so you can measure volumes. Then you have a measure here, and then you can put you have a measurable space here, and then your probability will be a probability measure, and all of these probability measures will form your ensemble space. If you are in quantum mechanics, it looks different than you have a projective variable space, those are your pure states, but then we consider all the mixed states, the density matrices. So positive, semi-definite, Hermitian matrices with trace 1 in finite dimension case at least. So we really don't talk about these, but we talk about the whole ensembles. Because this is really closer to what we have in real life. So then we put axioms on the space. So the first thing, as usual, is defining a topology, and this is where everything I talked about before comes in again. So also for an ensemble space, it must have a topology based on what is experimentally verifiable. So one of the first axioms is that it's a T0 second countable topological space. So then we already know what infinite operations and limits do and how they work. This will be all defined based on the topology. So what comes now basically are finite, and if you want to extend that to infinite operations, then the topology already define what limits exist and what don't. Okay, but really, the new axioms that I want to talk about are, for example, mixing. So this is one of the this is one that I already talked about in the first lecture, just to show our level of rigor. So you have seen that picture before. Uh, we can take two ensembles, mix them with a probability to get a new one. So we get a convex structure. So mathematically, this is just you take 2 points and then you can connect them in on that line based on the probability you get different points. So this is in principle just defined for two elements. Then you can just with extend that to finitely many. If you want to take infinite mixtures, your topology will tell you which of these do exist and which ones do not. Yeah, so basically right now what we have is we're at a topological space. Now we have a topological convex space, which is actually something not that well studied. There is a lot of mathematical theory about topological vector spaces, but we're not there yet. We have a topological convex space. And yeah, the next thing we put on top of it, which will add a lot of structure, even though it's quite like a somewhat simple axiom, is the axiom of entropy. And in fact, lots of the stuff I'm going to talk about is just like a vast number of consequences you get from just assuming this. So we have the idea that the things that you're talking about, the ensembles, are the collections of all the outputs of a preparation procedure. So we don't talk about the individual things, but we talk about the whole collection. But the collection is made up of things. And now we assume that we have a measure for how much these elements vary. So, for example, you might consider these two collections. So here, ensemble B, most of these elements are different. So you have 4 different elements, and if you randomly pick one, you will most likely get not the same as before. So if you look at ensemble A, most of these are the same. So the elements vary much less than the one in B. And we define an entropy as a measure of that kind of variability. Do the elements in that collection vary a lot or not? So the entropy is therefore a function that takes a given ensemble and then gives me a real number as a measure for the variability of the elements in that set. And it has a few properties. So the first one is strict concavity. So if we take two ensembles like this, A and B, then I mix them with some probability. I get a new ensemble and I look at its variability. Then in general, this can be bigger than just the average of these variabilities. So in the extreme case where A and B are just the same, mixing them doesn't do anything. So I will just end up with the same entropy. But when I mix ensembles that are not the same, well, then they will have different elements, or they occur with different frequencies. And then the new entropy, the new variability can only go up. That's strict concavity. And then we have, it can go up, but there is an upper bound. So the extreme case, where we have two completely different ensembles. So you have one here, and all elements here are different from all elements here. Then you have the extreme case where if you mix the two, the entropy goes up by the maximum, like maximum possible. So we assume there's an absolute, a universal function that bounds like by how much the entropy will increase, because and it only depends on this probability P, because in this extreme case, we have completely different elements in A and B. So basically, the output ensemble, whatever you get, you will immediately know whether it came from B or from A. And then this is what creates the additional variability, because you have, based on P, you randomly get something here or here. So there is some universal bound of how much the entropy can increase when things are completely different. Then we call these ensembles orthogonal. Then so orthogonal really means each of the elements in my collection are completely different. That also means it should be preserved under mixing. So if I have an ensemble A that is orthogonal from B, so these are all different. And then it is also orthogonal to C, so C has no common elements with A. Then if I mix B and C together, they still don't have any elements that were not in A. So you can't just mix and randomly get new elements that that might be in common with A. So this orthogonality, which happens when the entropy increases maximally, is preserved under mixing. Also makes a lot of sense. So those are the axioms that we put on this on the entropy, this function on the ensemble space. Well, I mentioned continuity makes sense. We talked about that before. So now I will go through what we can get out of just the fact that we have an entropy that can measure the variability of the elements in our ensembles. Well, we get a surprisingly rich structure from just assuming this on top of basically a topological convex space, just putting an entropy on it. So now I will go through basically a list of things that follow from just this. The first thing is that this upper bound that we said is on the increase in the entropy. Already has to be the Shannon entropy. And we haven't even talked about like any specific model of what these ensembles are about, but we already get exactly the Shannon entropy. So and it's not that complicated to arrive there. So we can go through the derivation for this and see how this happens based on the requirements that we put that I mentioned before, just the axioms. So first we will show that that we get the Shannon entropy basically for uniform distribution. So and then we will generalize it. So the first step is, let's say you have some sequence of orthogonal ensembles, and then you take a uniform mixture. So you take n by m, n times n many orthogonal elements, and you mix them uniformly. And then we basically use the trick that because of associativity, I can first I can mix them all with coefficients 1 over n times 1 over m, or I can first mix basically horizontally and then mix later vertically. Because of associativity, it needs to yield the same thing. So if you start with the entropy of this full mixture, you get since they're all orthogonal, you get this universal bound, and it has these coefficients 1 over n, 1 over m. So the coefficient on each individual ensemble, and then here you just get the average of the individual entropies. And if we split that into two steps instead, so we first mix these n elements, then you get just this function with a 1 over n. And then here you have to use the same expansion again. You write that out, So you end up here with, again, the average entropy, but now you have split this term into two. So here you had one term with a product basically, and now you have the sum with the individual fractions. So what you already get from this is that if you put in uniform distributions, basically this product here, 1 over n times 1 over m, turns into a sum of the individual ones. And then you already know, well, it has to be a logarithm. So it's the logarithm of these numbers with some factor in front of it, at least for uniform mixtures. And then the next step is, well, we can next consider rational distributions. So the probabilities are all rational numbers. And then because they are finite, we have like a lowest common denominator. So you can basically split this each of these AI into multiple of these based on, well, how many you need. So if you have a distribution like this, you find the lowest common denominator 1 over 15, and then all of these are just multiples of that. Then you can use basically the same trick as before. You either mix all of them together like this, or you first mix each of them as often as you need to get the appropriate probability that you want, and then you mix each row. So the trick is essentially the same. You use the associativity, you plug everything in and expand, and then then you compare with the original. So this is basically the final equation that we get. Here you got k log m. This is from the previous slide because you have a uniform mixture here. And then you compare that with this term here. And then on the next slide, I can show you, you just like rearrange this and you find out that this universal bound that depends on your probability distribution turns into exactly Shannon entropy. And then at some point you just pick constants such that we just choose logarithm and base 2. But yeah, this is the expression of the Shannon entropy. And the nice thing is that we didn't pick, for example, whether we have a classical space or a quantum space or anything. We just had like a very general ensemble space that would even capture things that are neither quantum or classical, but it's still always the same expression. So and it wasn't a lot of work. It's just very basic calculations. The full proof fits in 2 pages in the book. So yeah, we recover the Shannon entropy. And we only have one proof that works in all cases. We don't need to do it for classical and quantum separately. Talking about separateness, another interesting notion that we get straightforward from this entropy is that there is a difference between separate ensembles and orthogonal ensembles. What do I mean by that? We can say that 2 ensembles are separate if they don't have a common component. So this is based on the convex combination. So basically they are separate if there is no C, so some other ensemble, such that I can write both A and B as C mixed with something else. So they were basically there's nothing in common between them. They are separate. Once you define an entropy, you notice that the entropy gives you a different notion of or exclusive ensembles, which is the orthogonality that I defined before. Those ensembles that maximally increase the variability, so the entropy, when you mix them. And in general, it is true that if you have orthogonal ensembles, then they must be separate. But the inverse conclusion only holds in classical spaces. So in classical, you don't need to distinguish between these two notions. They are the same. They just say that your probability distributions have disjoint support. So you might think this one and this one, they're both separate. I cannot find a non-zero probability distribution that will be part of both. And also they are orthogonal. If you mix the two, the entropy goes up by the maximum, by the Shannon entropy. So, but in the quantum case, these are two different notions. So, we might want to consider three pure states, let's say. Then these are all separate. I cannot, a pure state cannot be mixed from anything else anyway. So they are all separate. But only psi A and psi B are really orthogonal. They are mutually exclusive. But like phi A and C, they are not orthogonal, which is also the notion of orthogonality, or in the Hilbert space sense. So yeah, just defining an entropy already gives you a criterion how to distinguish classical from quantum spaces, where these two notions coincide or they don't. So that's also very nice, like a very clear criterion that you get straight from the entropy to distinguish classical and quantum. And then we talked about convex spaces. We can take these mixtures. But once we have the entropy, we can basically start talking about vector spaces. So once you have an entropy, you can show that the convex space is what is called cancellative, which basically means if you have one mixture, A and E, and it leads to the same resulting ensemble, then by putting B and E with the same, mix B and E with the same coefficients, then this can only happen if A and B are already the same. So if you want, you can cancel the E on both sides, and I guess the P's, to show that A and B are the same. So this is automatically true. Like if once you put an entropy on that space, it will be cancellative. So then we can kind of invert in some sense. Well, in specifically this sense, mixing. And once you have that, you can start talking about not just convex combinations. You can start talking about, you can define affine combinations. So in principle, you could have negative coefficients. You just got to make sure that they each cancel, but now you know that there is a notion of canceling these on both sides. So they're not guaranteed that for all coefficients you will still end up in the inside the ensemble space, but it's still there are some affine combinations now with also negative coefficients that stay inside the ensemble space. So these affine combinations allow basically negative probabilities if you want. You still got to make sure you stay inside the ensemble space, but if you can cancel basically left and right all the negative terms, then you can use them basically temporarily. Anyway, we move from a convex space or convex combinations to affine combinations. And then you can basically start talking about differences. You can define differences between ensembles. So this is how we now move to a vector space. Once we have differences, they form a vector space. And once you define all these differences between ensembles, you can just basically pick a an origin for your vector space, and define all these differences, and then every ensemble is basically identified by an origin and the difference between your ensemble and the origin. So this is how we basically end up with an embedding of our original convex space in a vector space. So usually you like would just start by defining a vector space, which is much more convenient, and then say I might want to consider only a convex subset of that vector space. But if you want to justify that you have an embedding in the vector space, you start from what makes physical sense, which is only the convex combination. And then by putting more physical requirements, specifically the entropy, you can show that yes, you can embed it into a vector space. And you didn't need to assume like just that for convenience. There was really a physical requirement that we had to make them, namely that we can measure variability to see that this embedding into a vector space is possible. So yeah, but of course now it's still much more convenient to think about vector spaces when we need to prove anything. And then the entropy gives you even more. So for example, you can prove just because of the balance that the entropy gives you, that if you whenever you have a line in your ensemble space, which now a line is something you can now reasonably define because you have affine combinations now. Then it turns out that each of these lines will be bounded, so that we can even say a little bit more about how this convex space is embedded into the vector space. It will be bounded in each direction individually. That also comes straight from the entropy, and straightforward calculation. Okay, then there's the next block, even more things we can get from the entropy, which are really also one of the key motivating facts for why we want to define an entropy, which is that we can recover multiple different geometric structures across classical and quantum. So once we have the entropy, we can define some notion of distance. So if you have two ensembles A and B, you can mix them with just 50-50 coefficients, and then you can compare the resulting ensemble with just the average entropy of them individually. And so you measure how much did it go up. And this thing defines a pseudo distance. So I mean, if they are the same ensembles, then mixing them doesn't do anything. So you would just get the same entropy. So this pseudo distance will be zero. In general, it's then not zero. And well, it's bounded by one. It doesn't satisfy the triangle inequality. It's just a pseudo distance, but it does recover what's called the Jensen-Shannon divergence, which is defined both in classical and quantum. And while these are typically distinct definitions, we have one definition, and it leads to both specific cases in each specific context. Yeah, so just the entropy gives us already some notion of distance. And in fact, you can use it to define a metric on basically variations of ensembles. So if you take a small variation of an ensemble at some point, you can basically use that pseudo distance to measure its length. So basically that works because there will be only one like a norm on this variation. Then you basically have you can recover something like a metric for two vectors, kind of an angle, and that basically turns out to be like the second derivative of the entropy. And because the entropy is strictly concave, they always have a well-defined sign. So in that case, need to put a minus sign here, then this thing is positive definite. And it actually is something well known already. It's called the Fisher-Rao information metric. So that's a bit of a calculation to show what I said before. So if you expand the entropy, you have a small variation here. You expand to second order. Then if you take this basically mixing entropy, so where you compare the entropy of the two elements to their average, you go through the calculation, you expand each, the first order terms cancel, and you end up with a second order variation. And this then is this is then positive definite, and this therefore can be used as a metric. So that's the notion of distance that just comes straight from the entropy. And then we can also get measure theoretic structures also from the entropy. So for example, in classical mechanics, if you know the entropy is just for uniform distributions, it is just the logarithm of the measure of of a set. So in classical mechanics, you could start with a set, you know what it means to put a uniform distribution on it, and then the entropy would only basically depend on the size of the measure of that set. But what that also means is if you give me the entropy, then I can basically invert this. I mean, I just take the exponential, and then I can measure sets. I can also find out what the uniform distribution is. It's the one that's going to maximize the entropy out of all the measures that I can put that have support on a given set. So while like on a classical space, of course you start with a measure, you already defined it. But now I want to start with an ensemble space where I have only the entropy. And I just showed you like you can just invert this logarithm and you can start measuring sets using the entropy. And now we kind of we ask ourselves, can we define some kind of measure, a count of states, like on a general ensemble space where I only have the entropy, but just using the same pattern basically. Yeah, so basically what we had what the entropy measures is if you have it tells us how over how many distinguishable cases is our ensemble spread. So if you have basically small support of your distribution, it's gonna have less variability, less entropy than over wide distribution that has more cases because they're gonna vary more. So if you mix them, you get if they don't have overlap, for example, if they're orthogonal, it must increase. But that also means during mixing, if they can at most sum. So if I have completely well in a classical case disjoint or orthogonal ensembles, then I have completely separate elements in these, and if I mix the two, I can have at most these cases and these cases, but not more than that. So if we want to measure basically how many cases do I have, then these can at most sum. If you take the entropy and take the exponential, then you can show that this exponential at most adds up if you take two different ensembles. So this is basically our candidate for the measure, or this is our generalized state count. So It adds up at most, and you can actually also calculate exactly given two orthogonal ensembles for which probability will you achieve this exact additivity. So there's also all very straightforward calculations. You can find the p that maximizes it, and then you can plug that into the entropy to show. Then they do add up in the extreme case. So we have something that's in general sub-additive, and then it has, but it does always achieve for orthogonal ensembles this upper bound, and you can find out exactly where. So these calculations are not super long or complicated, and they will work in classical and quantum just the same way, which is very nice. So basically, the measure theoretic tool that we can get out of the entropy, we call it the state capacity. We want to measure how many states there are. Basically, generalization of like a Leo measure on a on phase space would be the classical case, which is what you need, for example, to do statistical physics, right? When you want to define well, when you have ensembles and want to do thermodynamics. So the general definition that we have is based on this entropy exponential of the entropy. So you can take any set, any measurable set on your ensemble space. You consider all of the hull is everything that you can mix based on this. And basically, the supremum here takes the uniform distribution over these cases. And then we do recover, once you take the supremum, we take the exponential of its entropy, you get state capacity. So this is really, it's a measure, it takes a set, gives you a number. It's non-negative. It's monotone, as you would expect. If you have a bigger set, then the state capacity can only increase. But in general, it is sub-additive. They do not always add up unless you have orthogonal sets. Exactly when you have orthogonal sets, state capacities add up. Yeah. So this is basically the setup. So we have like now a measure. We have a measure. It's just non-additive. But usually measure theory it's the basis of of probability theory. But the problem in general that you can see very clearly in quantum mechanics is that what we have so far are basically mixing coefficients. But we got to be careful not to confuse them with probabilities. So mixing is really you have different ensembles, different preparations, and you randomly select their output. But only in the classical case can you basically, if you want, confuse them with probabilities. So you can imagine you mix something like spin left and spin right, and that's all you mix. Those are the only components. You still get a non-zero probability of spin up, even though you didn't ever mix spin up in your preparation. So really, those are two different things, and but we still want to use to make the analogy as close as possible the measure theoretic tools that we're used to in classical probability theory. But now we have defined, at least we have a state capacity that's a measure, but it's non-additive. What would be basically the analog of these probability measures in general? So what we have defined is a fraction capacity. It's also a measure, it's also a non-additive measure. But what we can define in general is that if you have a given ensemble, E, And in general, you give it a set. Or if you want, like for a specific other element, you can define what is the biggest fraction that I can use here in front of A to create E. In principle, because there's a whole range of probabilities that I could put here. I don't need this ensemble necessarily. I could mix E with something completely different and A never appears, or I can use a lot of it. And we basically define this measure as the supremum here. In the classical case, everything reduces to the probability measures that you know. But in general, you can define this. But there will be non-additive. It's still a measure between 0 and 1, like probabilities. It's still monotone. It's not sub-additive. And it's still it has some continuity properties. And what this is, a non-additive measure, some people also call it a fuzzy measure. That's something people have studied before. Fuzzy logic, imprecise probabilities, that kind of stuff. So in here we naturally encounter this. And in fact, I've been at the conference last week where people talk about that kind of stuff. See if they could help us out to finish this idea. But that's all we have so far. So just to give you the key takeaways from the second part I talked about. So we had to talk about ensembles because we really talk about things that are reproducible. Then we were able to develop a theory of states and processes using these ensembles. We only put like a few justifiable starting points. We just had topology, of course, and then like convex structure that was very natural, and then we just put an entropy on it. But we already got a lot out of it. Then many of these definitions and proofs then do not distinguish the individual cases anymore. They are general. They work across classical, quantum, and in principle, even beyond that. Then we have really a generalization that links many different things. So we ended up with topological vector spaces, very foundational structures for functional analysis, for example. We found information geometry that is at the end of the day linked to symplectic geometry for classical mechanics, for example, but it also links to the inner product of quantum mechanics. And then, we found non-additive measures that generalize like the classical measure theoretic structure. So really, once you store additivity, everything is normal, but we have a generalization that is still based on measures. But there's still a lot of stuff to do. But yeah, we already have something quite solid. So to wrap up the whole talk, the whole second talk, actually also the first one, what I talked about was physical mathematics in general. So we really derived math straight from physical requirements. So we only develop math that's used to model physics. And we need to develop it ourselves to make sure that it has a physical purpose. Then we used different principles. Principle of scientific objectivity. We really talked about the evidence-based assertions. We had this notion of verifiable statements. It led us to topological spaces and sigma algebras. We could concretely recover the real numbers by giving specific examples of what kind of statements we're talking about. Then introduced the principle of scientific reproducibility. So that directly led us to ensembles. Then they have a topology because they need to be experimentally well defined. We need to be able to mix them. We got a convex structure. Then we have an entropy because we really have elements in that collection of an ensemble. We have like a very minimal measure on like just saying how much they vary, how different they are. And we immediately get things like embedding in a vector space, we get notions of geometry and measure theory just with that. So yeah, hopefully that's a good example of how much we can do with like very little assumptions with starting from scratch. So with that, we can go to questions.
And there were already a couple of questions, both, it's actually the same question from both YouTube and Zoom. Basically, how is it that we recover the reals instead of the rationals? So I'll take care of that. So the idea, yeah, if you can get one of those slides. So the idea is essentially is that it's the closure of the topology under arbitrary union that effectively functions as giving you a complete order. So a reference is essentially already something that it's cutting the space into something that it's before and something that it's after, right? So it basically cuts the space into two sets and in three sets. The extreme sets are open sets because they're open intervals. Now, what's going to happen is that if you have a set of references, you can do the union on one side to get limits. So, for example, if you have a reference, right, that it's where the before it's before 0 and the after is after 3, and then another reference that you still have before 0 and after 3.1, and then you have before 0 and after 3.14, and so on. So you get a sequence of that. Since you can make the union of all the after statements, you can effectively create a reference that it's before 0 and after pi. Now, if the condition of the denseness is not on the points, it's on the references, because those are the things that you can have. And so the order is dense in the references if you have two references and you can put a reference in the middle. If you have the rationals, you could have essentially between the statements after pi and before pi, there is nothing. Like you're missing the on, and therefore that's not a reference. So if you want to have a dense set of references, because the topology is closed under the countable union, you basically get the complete ordering, and that's why you are not you get the reals and not the rationals. So you basically have these two types of reference ordering. The one where you have sort of like immediate successor for references, and those are going to be the integers because you have these closed sets that are one right after the other. And in the real case, you have absolutely the opposite, that no reference have an immediate successor or immediate predecessor. And in the rational, you have this a hybrid case where if references are essentially touching or aligned on the same irrational number, you do not, you get the immediate successor and immediate predecessor, while if you are on a rational number, you don't get the immediate successor and immediate predecessor. So this, the ordering on the references is what basically gives you the rationals with the reals instead of the rationals. So I hope that makes some sense, but all of these things are, you know, in the proof of the books. It shows all these issues. Okay, so I think there is a follow-up. I don't understand how the construction accounts for the least upper bound property of ordered field R. So I think I would have to have a whiteboard at this point, which I don't have. So Imagine that every reference is a closed set and two open sets, right? And if you make the arbitrary union of sets that have some overlap on on that closed set, right? You are gonna get an infinite intersection. If it's an infinite intersection of closed set, you're gonna get something, and that's gonna be essentially how you get this Dedekind cut like thing, where you have a singleton and the two open sets of all the things before and all the things after, right? That's essentially how you recover them. And if you have these rational numbers, you're gonna end up with holes in the middle, right? You don't have anything, and so your reference in that case would not be a triple, because the on does not exist, and a reference must have that the on exists. Think there might be a video somewhere in my other channel where I go through some of these details. I
I mean,
don't know
we
if I
should
did.
have went through all of them in the reading group, right?
We did go through all of this in
It's
the reading group. Yeah,
recorded on, I think, on the same channel here.
yeah.
Yeah.
And again, it's one of those things that if I had a whiteboard, but I'm not really set up to do this
Yeah,
right
I
now.
mean, I was hiding all this on this slide.
Yes, exactly. Okay, you can go
So
and read. Okay, so let's this leave it at this. Maybe we, if we have more time later, we can discuss that even in more details. So let me go. There were some questions from YouTube. At what point ensemble spaces require direct input from physical theory, for example, a Hamiltonian? Do ensemble spaces put any constraint on permissible physical theories?
sorry, I didn't get that question.
Okay. At what point ensemble spaces require direct input from physical theories? Do ensemble spaces put any constraint on permissible physical theories?
Well, should put some constraints. Ideally, they shouldn't be too strong. If you violate any of these constraints, I would say your physical theory doesn't make a lot of sense. At what point does the ensemble space need input about the physical system? Well, so for example, I mean, so any specific ensemble space, of course, will need a lot of input on like what you are actually describing. So, for example, if you um if you talk about like a simple spin one half system, then your ensemble space will be the Bloch ball. Obviously, if you have a system with more states, it will be a higher dimensional something. So obviously, of course, the all the specifics of the ensemble space will depend on what specific system you have. Also, so at some next thing would be to define something like observables on that thing, and then you can calculate expectation values and stuff like that. And this will be depending on the specific system. And then also the for example, the specific topology that you put on that. Well, the topology has to be such that mixing is at least continuous, but otherwise, you might want, based on what things you can observe about your ensembles, that will define what you can experimentally verify. So that will determine your topology. Of course, in this talk, I only make like the absolute minimum requirement on what has to be on every ensemble space and show what follows from that. And I haven't given you any specific ensembles for a specific physical system. I'm not sure if it answers the question.
Maybe you want to talk about extreme points and whether they're in the ensemble space or not.
Yeah, so for example, in the classical, if you have a classical continuous space, uh, you have your probability measures. The extreme points on that space would be like Dirac deltas, where you have like you are exactly at one point. That's not physical anymore. I cannot verify that I'm there, but falsify that I'm there. Um, but yeah, this is all like needs then specific input from a physical theory. I don't have an example where like for the real numbers where I show, okay, this is the physical situation that I'm describing, you're gonna end up with the real numbers. I don't have an example like this uh for a whole ensemble space that I could give now.
Right, so the issue is really to find these bare minimum that every physical theory needs to get, and then it's up to specifying different assumptions or different constraints that would give us the specific physical theories. But we still need to figure out the basis. Um, let's get the next one from Zoom. How the sigma algebra is defined to ensemble spaces. Mathematically measure is a countable additive and non-negative set function from sigma algebra to reals.
Yeah, the same question is on Zoom.
Yeah, that's what I
Okay,
read.
yeah. I'm not sure if I understand the question correctly. So yes, probability measure is an additive measure that takes something from your sigma algebra, gives you a number. Um, um, yeah, I mean, yeah, this is still true. The thing I defined the fraction capacity is not a probability measure according to this definition, obviously, but it's still a measure. It's a set function. It's non-additive and so on and so forth. The ensemble space has a sigma algebra because I need to clarify what I can experimentally verify. Basically, I need to say, uh, what can I say about like in which ensemble I am? Can I verify that I am in one of these ensembles or not? Once I define that, I have a topology, then there's a unique Borel algebra, and then I have the sigma algebra on the ensemble space. That will be there. Um, and yeah, once I restrict that, essentially, no, and then yeah, then I have a sigma algebra, and then I define measures, and I can also define non-additive measures. Then I can also define additive measures. In fact, uh, there is a piece of mathematics called Choquet theory that will give me all additive measures that can represent an ensemble. That's a different topic, but yeah, we have all of that. We have sigma algebra that comes straight from experimental verifiability, and then measures, yeah, are set functions. And the one that I defined is not a probability measure, but it's still a measure. It's a
Yeah,
non-additive
I
measure.
think it's just that. We have a topology, we get the Borel algebra, and that's the sigma algebra that we use for all the additive, not additive measure for all that.
Yeah, I hope that helps.
Then another one from the YouTube chat. Are ensemble spaces already applicable to classical and quantum fields, or do they require generalization?
Okay. So we have checked that like the pretty sure that the classical mechanics, definitely classical discrete systems, and quantum mechanics do fit. For quantum field theories, I don't even know what the state space is. Like what space of field configurations they consider, I don't know. So I wouldn't even know how to check that what we have, like that what they have fits to what we have. I would expect that um, they will pick something that is like mathematically nice, and they're not careful that they don't include unphysical states. In fact, even for classical mechanics, we are concerned that it includes non-physical states. So, but yeah, whatever we're gonna do with field theories in the future, we will have to fit it into this because I mean, I just said required minimal things. Even for fields, I will still talk about something cardinality at most continuum, so that there is even a chance to measure to determine the state of the field. So whatever it will be, which I don't know, we will fit it into this key
Yeah, to
of the
be a little bit more precise, for classical and quantum, we know at least what, let's say, the space of states is, and we're still trying to finalize what is the correct space of probability measure, which is, at the end of the day, the space of ensemble, so the space of mixed states and uh, and the space of probability distribution in classical case. So it's still not 100% clear which is the correct one, also because there is the other structure that we still don't know how to put on, which is the Lie algebraic structure, the one that relates to Poisson brackets and commutator in quantum mechanics. That structure also needs to be there and needs to be well behaved and well posed, and we still don't understand how that works. And then once we will have all those things done, we probably will get a lot more sense of what are the actual physical and mathematical requirements for all those things. And then after that, we need to understand for field theories, both classical and quantum, what is the space of field configuration, which again, it's not exactly clear what it should be. And then what is the space of probability measures and the entropy associated with that that you put on field configuration. And quite frankly, that seems to be an open mathematical problem because when I talk to mathematicians, it's not clear that that has already an answer. So the good news is that the requirement that we're putting on the axiomatic basis that we have right now are so strongly physically motivated, and since the physics works, there has to be a way to make this work. Also, the pattern that both classical and quantum field theory have is very close to what you do in mechanics. So it's just a matter of having a mathematical proper generalization of the concept, which is essentially the piece that it's missing. So yeah, we need to do it, and we have little guidance right now.
The basic notion of ensembles is coming, as Tobias said, from the notion of scientific reproducibility. So the idea that science is about reproducible relationships between things. So that has to hold in general.
Yeah, if it doesn't hold, we might have a problem. And the last question from the YouTube chat was, so what needs to be done to complete the theory of ensemble spaces? It's basically what we just said, in the sense that part of it, it's finalizing the axiom that we already have. We know that there are some holes, and I'll talk about them tomorrow. For example, the axiom that we have for the entropy works well only if you assume that every ensemble that can be seen as a mixture of something can be decomposed into the mixture of orthogonal ensembles, of mutually distinct ensembles. It's not clear that this has to be the case. One could imagine a physical theory where that doesn't work, and one could also make some sort of argument that if you're doing quantum gravity, that's exactly what you're not going to be able to do. And then it means that we don't have a good axiomatic for the entropy, because the only 3-point constraint that we have, it's only when the three elements are mutually exclusive, when they are orthogonal. So in that part, we can't say anything, and you can also create things that I don't think should be physical, but the fact of thinking that something is not physical doesn't mean that you have a tight argument of what is it that the correct definition should be. And so there are some of these gray areas that needs to be cleaned up. And then, as I said before, the whole structure of the algebras and generators and all that needs to be generalized and needs to be properly physically motivated. And right now, we don't know exactly how to do that. So, which means more work, more opportunity for collaborations and ideas and stuff like that. So let's see if there are more questions. I always have to wait that all the lags on YouTube and people that are typing to make sure that there is actually no question. Okay, I don't think there are any more questions, so we'll end up for today. Thank you everybody for being with us, and tomorrow I'll present on the open problems that we have both in reverse physics and physical mathematics, and that's going to be the opportunity to discuss more if people want to participate and help us drive this program forward. Thanks again. Bye. See you tomorrow.